Okay, so thanks for the introduction. My name is Michael Jensch. I work for Siemens in Princeton, New Jersey. This is our research hub here for the US. As you know, Siemens is a German-based company headquartered in Munich, and we are the technology department. So we do research for our business units, and some autonomy, some robotics, a lot of industrial automation. And these things. So what I would like to present today is a project that was funded by ARM, and where actually Matt was even part of, as part of SWRI, and then we had other partners which are going to come to in a second. This project was finalized last November, I believe, and yeah, let me show you some of the details here. Right, interoperability. What is even the problem? I mean, in general, when we talk about the shop floor, we will have all these different controllers out there, right? We have maybe machine tool systems, we have robot controllers, we have maybe end effectors, we have cameras, we have edge devices, the cloud, we have process controllers, we have PLCs, and there's going to be interoperability between some of them, but definitely not between all of them, and usually not really out of the box. So what happens a lot of the time is that people, when it comes to the integration between these, you're going to create those point-to-point connections where you say, okay, I know what I want to do. I have this machine controller, and it has to be talking to this robot controller to tell the robot what it's going to be doing. The robot controller is maybe a Yaskawa robot, so I'm going to write a very specific connector between the two controllers, and it's going to work. But it's not really reusable. And next time we have a problem, we have to basically do it all over again. Maybe even if the interface changes, I have to add a parameter. I don't know what. It has to be done again by the same expert who has written the code. And it's in general, it's a pretty difficult problem to come across, and it's actually where a lot of the effort goes into when we talk about integration, or when we talk about commissioning of industrial shop floor problems. The dimensions of interoperability are essentially the 5 C's. This has been documented a while ago in a publication where we talk about the connections. So between two computing units, how do they find each other? The communication, essentially the protocols that are used to communicate between controllers or software units. Coordination, how do we even coordinate all the activities on the shop floor? Who tells whom what to do when? Configuration and computations are the 2 that we didn't really cover in this project. We concentrated on the first 3 that I mentioned. Again, why is it difficult? It's basically difficult because it's a lot of effort, and you need experts when you're talking about, especially when you're talking about protocol bridging, when one controller speaks one protocol and the other speaks another protocol, and you have to do this specific connector between the 2. You need an expert that actually knows both of those protocols, right? And that may already be difficult to find one. And then that person has to go and sit and write the code, and that is effort, and it has to be done. And sometimes this actually comes to several times the hardware cost is actually that integration cost. I already talked quite a bit about the one-off solution problem, that we have to do this over and over again. And of course, the whole technology can be pretty intimidating. Most of the time, these integration efforts would be done really on the shop floor by somebody and tested on the shop floor while the robots are moving and while the machines are there. So it's not really an environment where coding is very, very easy, and where you would be allowed to make many mistakes, right? So that's why that could be intimidating. What do we concentrate on in this project? So of course, on the one side, we have the robotic systems, which are pretty easy to interoperate when we have all the ROSs in play, because between ROS Industrial, ROS-I, ROS-II, it's pretty straightforward to come to an interoperability. I think, especially in this round, we all kind of know how to do that. But then when it goes towards the towards the other controllers, the other machines we have on the shop floor, it gets more difficult. We get exposed to, say, DDS as a middleware for integrating components. We have AntiConnect as a protocol to talk to especially machine tools, and of course we have OPC-UA, which is the common integration mechanism to integrate, especially on the industrial automation side, the hard industrial automation side, when we're talking about PLCs and these things. Yeah, sometimes we also want to talk to maybe simulation, robot simulation, industrial simulation environments, yeah, that is also covered in this project. So we had different tasks. We were looking at interoperability between ROS-I and DDS, between ROS-II and DDS. As we all know, ROS-II is based on DDS, but is it really easy to write a DDS component, native DDS component that is able to talk to a ROS-II action server, exchange messages, whatever you want to do? Before the project, we believe it was not, and we made it quite a bit easier. So that's where we spent some effort. And also, of course, the interoperability between DDS and OPC-UA is something we looked at very, very deeply in this project. The partners on this project, as I haven't said it yet, were RTI, so a DDS vendor, or the most prominent DDS vendor. Swiri, I already mentioned. Siemens, that was us. Schlumberger was in the boat, Yaskawa, and I don't think Kiba was there in the end. That must have been an older version of the slide. So let me explain what we did. I was talking about the interoperability between OPC-UA and DDS. So essentially, a gateway was developed which can be configured. So you don't have to really write this point-to-point connection. You just have to instantiate that gateway and basically engineer it. It makes it already a whole lot easier. You have to engineer it, which OPC-UA tags you want to map onto which DDS topics, essentially. There was a previous implementation which was pretty basic, only Linux, only unidirectional communication. There was a standard actually already out, but implementation wasn't quite there yet. So this was robustified. We had bidirectional communication at the end. Linux and Windows was available. This is now part of the RTI product suite. So it can be made usable if you have an RTI DDS license. We have DDS. We were looking at DDS and ROS-II interoperability. As we know, as I explained before, also ROS-II is based on DDS. But what does it really mean? How to do that? How to write a DDS component that natively talks to ROS-II? I mean, why would you even want to do that? Essentially, if you want to write your ROS components, you always have to be in that, and your ROS-II component, you always have to be in that workspace. You have to define your specific actions and messages and all of these things. And then you can build it within your ROS-II workspace, and then it's a very integrated solution, as we all know. But maybe that's not possible. You want your native DDS devices and so on to talk to your ROS-II applications. This has been investigated and by RTI as well, by the way. And it was made possible, and they have documented that, and it should also be available to everybody. It's a product of the project here. Finally, AntiConnect is not only a communication standard, it was also an implementation on how to work on this coordination problem that I was explaining earlier. Before this coordination, and I'm going to get into a little bit more details on the coordination aspect here of AntiConnect, it was hardly coupled to this HTTP transport. And this was moved completely to have a standalone AntiConnect Python package. And we put it actually onto DDS so to make the communication much more flexible. So with this, you can now have a pretty high level coordination in your shop floor. And this Python package can be easily also extended towards maybe new protocols, different APIs, and all of these things. But this high level coordination is already out there. This was driven quite a ways further in this project as well. And then finally, we have also integrated a cloud and simulation via OPC-UA in this case. So we were able to integrate a process simulation tool from Siemens which already has an OPC-UA client, via this OPC-UA DDS gateway into this coordination scheme. Altogether, this is basically a toolbox that people can now use and has been made available, and that people can now use to make this very difficult interoperability problem much more easy and accessible, by just picking the right tools from the toolbox and using them for their needs. Right, I was saying AntiConnect coordination. This AntiConnect coordinator is quite neat. It is distributed, has a distributed scheme of operation, and essentially these distributed orchestrators, they advertise their skills, their tasks that they can execute via topics, and we've chosen to put this on DDS because it's pretty straightforward to do that, since DDS is based on publish subscribe. And then they would sort of talk to each other and see who can do which task. And by this distributed scheme, it also scales pretty well. And then, as I was saying, from this AntiConnect orchestrator instances, which are distributed, you can use the Python extensions, or you can easily extend it to, in the easiest case, just use some proprietary protocols or APIs or whatever to talk to anything you want to. But that is still pretty basic, and it's still this kind of point-to-point connection. So on the next level, you can have your AntiConnect over HTTPS still, as it was there before. So if you want to talk to, say, your CNC machine, which supports HTTP, we showed how it can be used to talk to any ROS or ROS-II device or robot, of course. And then finally, when you're talking to your PLCs or industrial software, which are offering their services via OPC-UA, you can use this OPC-UA to DDS gateway. Then I'm going to quickly explain the demo use case. So due to COVID, we had to strip down the demo use case a little bit. It was not possible to run on the real shop floor because of all the restrictions that we all had at the time. And but we still wanted to pick something which is complex enough to make it believable that this is a real life scenario. So we had a complex industrial environment where we had industrial simulation software, we had cameras and sensors, we had real robotics, robotic arms, which were controlled via ROS or ROS-II. We had our industrial controllers in place, and we had an industrial grade transportation system, which was essentially a linear motor-based transportation system. So we could transport the materials from one station to the other. Of course, with the simulation and the robotics, that's where this scenario was we had to, you have to have some imagination on how to see how this could really play out. But we believe from a technical perspective, we were really able to showcase the interoperability that we wanted to showcase. Manufacturing process that we chose was pretty simple. Basically, raw material needs to be supplied to the overall factory floor. Then it needed to be milled, then welded, then polished, and then the quality inspected at the end, and you get your finished material. So you basically go through this linear process. When we look at how this was implemented in the using the AntiConnect coordination, you get an understanding of how this AntiConnect orchestrator would really work. So we had the PLC, which was essentially that supply station, or which mimicked that supply station where you would supply the product or the raw material to the factory, would drive the overall process. And so it was sort of like the line controller on the factory floor. And it would ask basically, can somebody help me with milling this material? And the simulated CNC would say, oh yeah, I can do that. But I need somebody to actually load the material into me so that I can mill this. Robot would say, oh yeah, I can do that, but I need somebody to transport the material to me. And then the transport system would say, okay, yeah, I can do that. And then the whole recursion would go back, and loading would happen, milling would happen, unloading would happen, and then go back to the PLC. Essentially, then the welding happens, the polishing happens, the welding happens, and the inspection happens at the end. So this is how the whole coordination worked. So from an integration perspective, we were showcasing all the different aspects, the orchestrators, the Python implementations of the orchestrators. would essentially talk to the OPC-UA server in the PLCs via this DDS to OPC-UA gateway. We had a similar setup for process simulate, where it was essentially reversed. We had the client in the process simulate, the server in the gateway. So that, of course, on the in OPC-UA makes a big difference. We had our DDS to ROS-I interoperability to show to coordinate or to integrate our machine tending robot. We had standard ROS, not ROS-II, to do the welding robot. We had inspection, which was just using a simple API from the Python from the Python orchestrator to the computer vision application. Another ROS-II, not ROS-II, ROS node, and at the end, this native AntiConnect device, which was an emulated CNC going forward. I think I'll quickly jump over this. This was, sorry, no, I'm too quick. There we go. This was actually a neat feature of DDS. Due to COVID, we had some additional restrictions. So essentially, we had one of the robots not stationed in the same location where the rest of the factory was. So this robot was really placed in Berkeley, and the rest of it was in Princeton, New Jersey. So really on opposite sides of the coast of the country. We were still able to run the whole coordination via DDS, basically via the WAN system, via the internet, using a VPN between the two. And it was pretty easy to use this DDS middleware to run across VPN, even discover the universal robot was there with its AntiConnect orchestrator, and then trigger the actions on this universal robot for the welding application. I can quickly show you the overall demo, how it then came to be. Essentially, what you would have just seen was the supply of the raw material to the transport system, and then we had some additional for explanation. We had some additional delays in here. The transport system would drive it to the robot to be loaded into the simulated CNC, and then we had some interaction between the robot orchestrators. And then you see a little window of the simulated CNC down here. This is process simulator, Siemens simulation tool for process simulation. And you would now see the milling starting in a second. So doors close, milling happens. And then from there, when this is done, the robot would take the part again out of the simulated CNC machine. Again, all of this happens across multiple protocols, and always via these tools in the toolbox that I was explaining earlier. Otherwise, this demo might not be even too exciting to look at. Okay, there's a robot doing something. There's a transport system. Okay, why is that interesting? But if you imagine how many protocols are involved in the background and so on, that's what makes this more interesting. Then we jumped over to Berkeley. And here we see the welding part going on. So here in the background, what you see is basically this AntiConnect orchestrator receiving the commands. We see some the welding simulation happening. This is actually another ARM project, which was finishing just about the same time as this project. So we were reusing the outcomes of this project and really triggering their robot demo from our overall scenario and the overall orchestration scheme that we had. And then when this is done, this would go back to Princeton, and at the end, we still have a little, I'm just scrolling forward a little bit. We still have a little machine tending operation happening, where this is now the AntiConnect emulated CNC. You have to imagine a few things here, and the robot doing a machine tending operation here in the background. Just summing it up, we have developed and hardened open source software based on open standards. all these tools that were developed are usable and can be integrated in your overall interoperability problem. Essentially, we successfully de-risked these communications, and especially the interoperability between them. We developed this reusable software, the AntiConnect Python package, which is available from SWIRI, and everything is accompanied by tutorials, documentation, and samples for all core software contributions. Finally, little TRL journey, as we called it. So essentially, we were able to drive the TRL levels on the RTI gateway, essentially the DDS to OPC-UA gateway, quite a ways up in this project. The AntiConnect orchestrator the same, and the ROS-I integration with DDS. And we are continuing our work with ARM at this point, and reusing some of those in new and upcoming projects, or currently running projects even. Yeah, stay tuned for more on some of these new interoperability projects. Yeah.